Okay, so today we're going to solve some systems of inequalities. If you remember from your Algebra 1 days, we're going to do a quick refresher here. An inequality is a lot like an equation when you go to solve it, except you're going to have multiple points that are solutions instead of just one. So if you are trying to write an inequality to match this graph, you can use your slope and your y-intercept. So if you look at your y-intercept here, it's crossing your y-axis at 5. If you want to do slope, you could either do y2 minus y1 over x2 minus x1, or you could just do rise over run, which is going to be a little bit easier. So if I just look at how I get from that first point to my next point, I'm going up 2 into the right one. So my slope should just be positive 2. So if I was going to write an equation for the boundary line on this graph, it would be y equals 2x plus 5. But since it's an inequality, I'm either going to have y is greater than 2x plus 5 or y is less than 2x plus 5. So if you look at the shaded region on this graph, it's below your boundary line. So that means it should be y is less than 2x plus 5, because it's all the ordered pairs where if you plug in their x and y values, it's going to be below that line. If you want to check just to make sure that it matches your shading, you could plug in one of the points in the shaded region, like I like to plug in 0, 0. Since 0, 0 is on the side of the line that's shaded, it should make our inequality true if our inequality is correct. So let's do a quick little check here. If you plug in 0, 0, you're going to have 0 is less than 2 times 0 plus 5, which gives you 0 is less than 5. So that makes our inequality true. That means that we're good to go on this less than right here, since it made our inequality true when we plugged in a point in the shaded region. You'll also notice that we just did less than, not less than or equal to. That's because the boundary line is dashed and not shaded, or not solid, sorry. So if our boundary line had been solid, instead of dashed, we'd do or equal to. But since it's just a dashed line, all the points that are below that line are going to make that inequality true, but not the actual ordered pairs that are on that line. So that inequality should match the graph that we've got. System of inequalities is just 2 inequalities, or 3, instead of a single inequality. So if you want to know if a point is going to make a system of inequalities true, it has to make all of the inequalities true statements when you plug in your x and y values. So if I'm going to take and look at the system of inequalities that I've got here, if 0, 0 is going to be a solution, it will have to be true in both of those inequalities. So if I want to check to see if this is a solution, take your first inequality and actually plug in x and y values of 0. So if I do y is greater than 2x plus 1, and plug it in, I've got the statement 0 is greater than 1. 0 is not greater than 1. So that point 0, 0 is not going to be a solution to our inequality system of inequalities. It might work in the other one, but in order to be a solution to the system of inequalities, it would need to work in both. So if it doesn't work in both, then you don't even have to, it doesn't work in one, you don't even have to test it in the other. It's not going to be a solution. If you take 2, 7 and plug it into that first inequality for your x and y values, this time your y value is 7, x value is 2. If you try that, you've got 7 is greater than 5. That is a true statement. So we're kind of halfway there. It has to work in our other inequality as well if it's going to be a solution. So we'll try it in that second one. And that'd be 2 plus 2 times 7 will give you 14. Gives you 16 is less than 18. That's also a true statement. So since it makes both of those inequalities true, 2, 7 is a solution to that system of inequalities. Last point's 4, 6, so if we try it, and y is greater than 2x plus 1, we've got 6 is greater than 2 times 4 plus 1. But that gives you 6 is greater than 9. 6 isn't greater than 9. So 4, 6 is not going to be a solution. So if you want to check and see if individual points are a solution to a system of inequalities, you just need to plug them into all of the inequalities in your system and see if they make all of them true. If there's even one that's not true when you plug it in, then it's not going to be a solution to your entire system. Most of the time, though, we want to figure out all of the solutions to our system of inequalities. We don't just want to check random individual points. So to determine all the points that make your system of inequalities true, you're going to want to just graph each inequality individually. And then if you look at where your shading overlaps, that's going to be the solution to your system of inequalities. So you would graph your inequalities just like you would normally. So if you're looking at like y is less than 3x plus 2, it's already in slope-intercept form, so on your y-axis, you could put a point at 2, slope at 3, you're good to go on that one. Let's go ahead and change the second one to slope-intercept form. So if you divide by a -1, you're going to have y is, it'll flip the direction of your inequality since you're dividing by a negative. Anytime you multiply or divide by a negative value, change the direction of your inequality symbol. So we're going to end up with y is greater than -2x. Now they're both in slope-intercept form, so let's plot them on our graph here. Okay, for the y is greater than 3x, or y is less than or equal to 3x plus 2. Excuse me. You've got a y-intercept of 2, slope of 3, so you're going to be going up 3 and to the right 1 to get to your next point. Gonna have to go backwards a little bit too here. This is an or equal to, so it's going to be a solid boundary line. So if we go ahead and connect those, there's your boundary line. Now either all the points to the left or the right side of that line are going to be your solutions, but we don't exactly know which ones. So if you want to determine which half of the line to shade here, you could plug in a point and check it. So if I test a point like 0, 0, I like to plug in 0, 0 because it's easy to test. You're going to have 0 is less than or equal to 3 times 0 plus 2, which just gives you 0 is less than or equal to 2. That is true. So where 0, 0 is, that half of your plane is going to be a solution to your system of, or to this inequality. So 0, 0's on this bottom right side of your line. So all the points on that half of your plane are going to be solutions to that inequality. So we'll shade over there. You can also kind of look the way it's set up. If it's less than, it's going to be like below your line for your solution set if y is on the left-hand side. But sometimes it's a little hard to tell what's below and what's above. So you can just plug in a point and try it. For this second line, y is greater than -2x. Your y-intercept 0. Slope's -2, so point at 0, 0, down 2 into the right 1 to get to your next point, since my slope's -2. This time it's greater than without an equal to, so your boundary line's going to have to be dashed instead of solid, because you're not including the points on your line in your solution set. I hate drawing dashed lines. Okay, something like that. And again, you're going to have to decide where to shade at. So I'm going to test a point in that inequality. I can't use 0, 0 because that's actually on my boundary. So I'm going to test 1, 0. So if I try 1, 0 in my original or the one I solved for y, it doesn't matter. I'll just plug it in the original. I'm going to have -0 is less than 2 times 1. 0 is less than 2. That's true. So where 1, 0 is going to be a solution. So 1, 0 is right over here. So all the points on that side of my boundary line are going to be solutions to that inequality. So if you look at our shaded region on our graph, the green part's the solutions to that second inequality. The red part's the solution to our first inequality. The overlapping part, where they're both shaded, is the solution to the system of inequalities that we actually want. So I'm going to make it nice and dark. All the points in that region are going to work in both inequalities and make them both true. So that's truly your solution set to your system of inequalities, are all those points. You could even erase the individual shadings if you want to, and just leave the solution set shaded. So there you go. And let's do a few different kinds here. If you look at this one, this first inequality is a little bit odd. It's a compound inequality. You could think of it, if you want to, as two separate inequalities that say x is greater than or equal to 1 and x is less than or equal to 4. Those are both vertical lines for your boundaries since they're x equals. So if you draw in the two vertical lines through the x values of 1 and 4, this inequality consists of the points with x values between 1 and 4. So your solutions to that inequality are all those points with x values in between 1 and 4, between those two lines. Again, it's solid because these are or equal to's. Your second one, y equals, is going to be a vertical, or not a vertical, horizontal line instead. So all the points with y values of 2 would be your boundary line. And shading wise, it's actually all the points with y values less than 2, which would be the ones that are below that line. If you think about coordinates of points with y values less than 2, y values are getting smaller as I go down here. Okay. And then the solution set to that system of both inequalities together is this little rectangle where our shading is overlapped at, right in there. So any of those points in that region would make both inequalities true. Go erase my extra shading. Going to have a few quadratics instead of just straight lines. So if you look at this first one here, you could do x equals -b over 2a to get your vertex, or you could think about the fact that it's not shifted left or right since it's just x squared. It's not shifted up or down either. Either way you do it, your vertex is going to be at 0, 0. We've got a vertical shrink going on, but no other transformations. So besides our vertex, we always need a few additional points when we're graphing quadratics that we can then reflect over. So if I pick like x values of 1 and 2, and plug them in. Plug in 1, I'm going to end up with 1/2. Plug in 2, square it would be 4. Half of that's going to give me 2. So let's plot that quadratic. 0, 0, 1, 1/2, 2, 2. Reflect them over your axis of symmetry. This is a greater than or equal to, so it's going to be solid line when you go to connect it for your boundary. Again, I need to know which side of my line to shade on, whether it's kind of below and outside or above and in between here. I can't try 0, 0 because that's on my boundary, so let's do 0, 1. So if I try 0, 1 in there, I'm going to have 1 is greater than or equal to 0. That's true. So 0, 1 is a solution. 0, 1 is right there. So all the points that are inside and kind of above my boundary line are solutions. If you look at your second one, it's just a straight line, slope of 2, and a y-intercept of 2. So y-intercept, and then up to right 1. This should be a dashed line because it's a less than without the or equal to. So draw yourself in a dashed line there. And then if you're figuring out where to shade, it's a less than one, so kind of rule of thumb should be below, but let's try a point in it just to make sure. 0, 0 is not on that line, so I'm going to test it. Plug in 0, you get 0 is less than 2. 0 is less than 2. So we're going to shade the region where the point 0, 0 is. 0, 0 is down here, below my line. So there's my solutions to that inequality. And again, the solution to the entire system of inequalities is my overlap. So that's this little sliver in the middle here. So I'm going to erase my extra shading. All those points should work in both inequalities. Last one's another quadratic. So if you look at this one, it's in vertex form, so it's shifted left 2 and up 1. So my vertex is going to be at -2, 1. Going to need some additional points as well. So if I do like -1 and 0, plug in -1, you're going to have 1 squared, change the signs, -1, add it to +1, 0. Plug in 0, that'd be 2 squared, it's 4. -4 plus 1 would be -3. So if I plot that, here's my vertex, -1, 0, 0, -3. Reflect across my axis of symmetry. Solid line on both of these here. Ooh, it doesn't look like it goes through my point, but it's supposed to. And then if I test a value to see what my solutions are, I'm going to do 0, 0. If you plug in 0 for x and y, you're going to end up with 0 is less than -3. That's not true. So 0, 0 is not a solution to this system. Since 0, 0 is like over here, that means I don't want those points. I want the others kind of inside and below my quadratic. So since 0, 0 doesn't work, shade the other region instead. Your other line is y is greater than or equal to 3, so that's just another horizontal line. All the points with y values of 3 or larger. The ones with y values that are larger than 3 are going to be above that line. So your two inequalities solution sets don't overlap. There aren't any points that make both of those inequalities true. So this is actually a system of inequalities with no solution. You can get some points that work in one, some points that work in the other, but there are no points that are going to make both inequalities true at the same time. So it's kind of the big idea. You're just graphing some inequalities and seeing where they overlap or not. That'll give you your solution set for your system.